Today our lesson is going to look at the acids and base properties of salt solutions. So again, we have to first start off by understanding what the definition of a salt is. So in this case, we're not just going to look at sodium chloride and potassium nitrate and things like that. Those are all definitions of salt, but what actually happens is sometimes these salt solutions will actually affect the pH and have some acidic or basic properties. So we're going to look at each one individually, and hopefully you guys can sort out which ones have acids and basic properties by the end of the lesson. So I'll just minimize the recording. So to start off, the pH of salt solutions, where does it come from? Well, first off, when we look at a salt, we know that it will dissociate into its ions. So here's an example that I gave you of ammonium chloride, and it dissolves or dissociates into its ammonium ion and the chloride ion. Some of these dissolved anions and cations will react with water. When that happens, it will affect the pH of the solution. So I'm not going to tell you why this happens quite yet. I'm just going to sort of show you a brief overview of what happens, and then we'll get into the rules so that you can figure out when this does happen and when it doesn't happen. So if the anion, so the negative, or the cation, the positive ion, react with water, it can change the pH of the salt solution, and it will change it to be either acidic or basic depending on how the ions react with water. So in this case, what you're going to start to ask yourself is, you're going to take any salt and you're going to write out the dissociation equation just like I did at the top of the slide here. Then you're going to ask yourself, do NH4 plus or Cl minus or both, do they react with water? In this case, I'm going to give you the answer. Now, I know you don't know how to figure out the answer yet, but I'm just going to show you an example of how this would look. So in this example, your chloride ions will not react with water. So when it reacts with water, when you put chloride ions in water, basically you end up with the same thing, or you end up with no reaction. Why? You don't know that yet, but you'll figure it out in a couple of minutes. So just bear with me for a second. The NH4 ion, on the other hand, will react with water. Yes, it will. And here's what happens. The NH4 reacts with water. NH4 has an extra proton to donate to water. So remember that a proton donor acts like an acid. So in this case, your ammonium ion is acting like an acid and donating a proton to water. What's left? Well, NH3, because it got rid of one of its protons, and now we have H3O+. So if this is happening, you can see that when your ammonium ion reacts with water, you make new products, NH3 and H3O+, and because we're making H3O+, this solution is actually going to be slightly acidic. All right, so I gave you the answer for this reaction. I said that NH4 reacts with water, but your chloride ion does not. So now, how can we actually figure this out? Well, this reaction with water, first off, we're going to go through some new terms with you, and then I'm going to show you how to figure it out. So the reaction of the cation or the anion of a salt with water to produce a change in the pH is called hydrolysis. So in this case, my NH4 reacted with water and made some hydronium ions. That will decrease the pH or make the solution more acidic, however you want to look at it. So your new terminology is right down here where I'm putting this star. We can say that the ammonium ion undergoes hydrolysis or that it hydrolyzes water. So both of those words you're going to hear a lot for the rest of the unit. So thus a solution containing an ammonium ion will be weakly acidic. Great. So which ions will undergo hydrolysis? These are your rules. There are 4 of them. Unfortunately, you have to memorize them. So rule number 1, group 1 and group 2 metal ions do not undergo hydrolysis. The only exception to that is beryllium. You don't really need to know why until I think about second year chemistry. So all you need to know is that beryllium is the exception and beryllium will undergo hydrolysis. But for this course, I'm not going to give you beryllium as an example. So if you have a group 1 metal or a group 2 metal, no hydrolysis is happening. Rule number 2, if an anion is the conjugate base of a strong acid, it will not undergo hydrolysis. Ugh. All right, so let's decode this a little bit. If the anion, so the negative ion, is the conjugate base of a strong acid. So here, I've basically given you a chart with a bunch of strong acids, HCl, HBr, HNO3. Its conjugate base, or the anion that goes with it, are here. So you can see each one of these are circled. The only difference between them and their acid pair is that they have one less proton. So they're a conjugate acid base pair. That's a little bit of review for you. Okay, so if Cl is your negative ion, your conjugate acid is HCl. These are all strong acids. Now, you should be able to know by now how to determine if an acid is a strong acid or a weak acid. How do you figure that out? You look at the chart in the back of your textbook, your Ka chart. If you have a very, very large Ka, you have a strong acid. So you'll see in that chart that sometimes they don't even give you a Ka value. They just say it's really, really big. Those are your strong acids. If you have a smaller Ka, or if they actually give you a Ka value in the back of the book, that means it's considered a weak acid. So if you're not sure, look in the back of your book. If it has a very high Ka, or it doesn't say, it just says very, very large, you know it's a strong acid, and you know its anion is not going to undergo hydrolysis. So none of the anions, none of the negative ions in this chart will undergo hydrolysis. So in both of these cases, for both of these rules, there's no reaction for the hydrolysis. Okay, rule number 3 is the first rule where you will undergo hydrolysis. So a negative ion, or an anion, will hydrolyze water if it's the conjugate base of a weak acid. So now check out my column here. These are all weak acids. And I can know that because I looked at the back of my textbook and I can get a Ka value. So when I look at my anion that goes along with it, these will all undergo hydrolysis. Okay, now here's something that you have to keep in mind when you're doing this. If we're looking at the anion undergoing hydrolysis, we have to find a Kb because they're going to act like a base. So to find the Kb, I'm just going to erase that arrow that I just drew for a second. To find the Kb, when you look in the back of the textbook, you're only going to get a Ka value for the weak acid. So to find the Kb for the anion over here, you have to do Kw divided by the Ka from the back of the text. So I'm going to go through an example of that with you later on, okay? Here's an example of an anion that will undergo hydrolysis, and look what happens to it. So if you look at NO2, its conjugate acid is HNO2. If you look that up in the back of your textbook, you learn that this is a weak acid, Wa, weak acid. So now I know that the NO2 minus ion will undergo hydrolysis. So when it does that, what's it going to do? It either has to gain a proton or lose a proton. Well, if you look at NO2, it doesn't have a proton to lose, so instead it will accept a proton from water, so therefore it acts like a base. And that's how I get HNO2 in my product side. What's left over from my water molecule? OH, because I got rid of the hydrogen and I put it on the NO2. The Kb for this reaction is 1.4 times 10 to the negative 11. How did I figure that out? I found the Ka for HNO2 in the back of the text, and I knew that Ka times Kb was Kw, so I rearranged my equation just like up here, and I calculated the Kb. So I did 1.0 times 10 to the negative 14 divided by the Ka in the back of the textbook, and I get 1.4 times 10 to the negative 11. Okay, last rule. A cation will hydrolyze water if it's the conjugate acid of a weak base. So again, its base over here has to be weak. How do you figure that out? Use the chart in the back of the textbook. Don't be lazy. So there's my weak base. When I look at my conjugate acid that goes along with it, these are both examples of cations that will hydrolyze in water. Okay, so again, my example is NH4. According to my rules, this will undergo hydrolysis. So here's my hydrolysis reaction for NH4. NH4 was overly generous and donated a proton to water. So because it donated a proton, it's considered an acid. and I end up with H3O plus at the end and NH3. When I look this up in the back of the book, there is only a Kb for my NH3. There is no value for Ka for NH4. So what do I do to find my Ka? I use this equation right here. So we will do actual examples of that right now. All right, so let's go through a couple of examples. Will each of these ions undergo hydrolysis, or will the solution be acidic, basic, or neutral? So the first solution, so when you're doing this, follow your steps. Step 1, if you have a solution of NaCl, you have to write out the dissociation equation. Now, I've done it here for you, but you have to not be lazy and make sure you've got that. So you split it up into its ions to write out the dissociation equation. Then you look at each one of the ions that it makes and tell me whether or not it undergoes hydrolysis. So look at Na+. Will this undergo hydrolysis? Your answer, it will not undergo hydrolysis. Why? Because it's in group 1. And according to rule number 1 that I gave you, all the elements in group 1 will not undergo hydrolysis. Now look at your Cl. I'll do this in green. Will this undergo hydrolysis? It will not. Why? Because it's the anion for HCl. HCl is a strong acid. So because of that, it will not undergo hydrolysis. If you really want to know why, I'll take a second to explain it. Because HCl is a strong acid, if I try to write out the dissociation equation for HCl, Cl minus and H plus, you're going to see that basically, because it's a strong acid, it's going to 100% dissociate into its two ions, which means that when Cl tries to undergo hydrolysis, it's never going to make any of this because it's just going to dissociate again. Okay, so that's the reason why. Or you just know that because HCl is a strong acid, that's rule number 2, it will not undergo hydrolysis. That in itself is reason enough. So what's the pH of this solution going to be? You have no hydrolysis, no change in pH, so this resulting solution is going to be neutral. All right, let's do the next one. A solution of KNO2. So again, step 1, write out your dissociation equation. KNO2 dissolves and splits up into K plus and NO2 minus. Now you look at each one of the ions and decide if it's going to undergo hydrolysis. K plus, will it? No, it will not. Why? Again, it's in group 1. And according to rule number 1, group 1 ions will not undergo hydrolysis. What about NO2? NO2's acid that goes along with it is HNO2. This is a weak acid. So it will undergo hydrolysis. Yes, it will. Great. Now, how do you determine from that if this reaction is going to be acidic or basic? Check this out. Here's what you do to figure it out. You have to write out the hydrolysis reaction. So let's practice this now. You're going to take this ion, NO2, because that's what's made from KNO2. So you're going to take NO2 and write it down. Then you're going to add water to it. Then you're going to see, is it a proton donor or a proton acceptor? In this case, it doesn't have any protons. It doesn't have any H's to donate. So it's going to accept a proton from H2O, and it's going to make HNO2 and OH minus. Because of this OH minus, the solution is basic. Okay, let's go through 2 more examples. Here's a solution of ammonium nitrate, NH4NO3. How do you figure out if it's going to be acidic, basic, or neutral? Again, write out your dissociation equation. Split it up into its ions, NH4 plus and NO3 minus. Then look at each one and decide, is it going to undergo hydrolysis? NH4 is the conjugate acid of a weak base, NH3. Yes, it will undergo hydrolysis. Okay, that's according to your rule number 4. NO3 is the anion that goes with HNO3. And if you guys look up HNO3 at the back of your textbook, you see that this is a strong acid. So this one will not undergo hydrolysis, no. So now how do you figure out if it's going to be acidic or basic? You know one of them will undergo hydrolysis, so you have to write out the hydrolysis for that ion. Here's my ion, NH4+. Straight from my dissociation equation, I write that down, NH4+, and I add water to it. Then figure out what's it going to make. NH4+ has an extra positive proton to donate to water, so it's going to act like an acid. It's going to make NH3 because it got rid of a proton, and now my water has the extra proton and makes H3O+. This makes it acidic. All right, last one, a solution of CH3COONH4. So you basically got ammonium acetate in there. What do? Same steps as always. First step, break it up into its two ions, CH3COO- and NH4. Then look at each ion and determine, will it undergo hydrolysis? So let's look at the first one, CH3COO-. Its conjugate acid is CH3COOH. That is a weak acid. So this one will undergo hydrolysis. Now let's look at NH4. Well, NH4+ goes with the weak base, NH3. Uh-oh, this is also weak. So will this undergo hydrolysis? Yes. Awesome. So I've just thrown a little monkey wrench in your plans. And now you have two ions that will undergo hydrolysis. So can you figure out if this solution will be greater than 7 or less than 7? Will it be acidic or will it be basic? Let's go through it and see. What do you have to do? Same thing you've done before, except now you've got two hydrolysis reactions to write out. So we're going to do the first one in red. I'm going to take this ion here and show what happens when it dissolves in, or when it hydrolyzes, sorry, in water. So if I have CH3COO- and I add H2O to it, it's going to accept a proton and act like a base. And we're going to make, I'll write it like this, CH3COOH plus OH minus. So if I just had that happening, I could say that this reaction is going to be basic. But I don't just have that one happening, I also have my NH4 hydrolyzing. So I write that down. NH4 plus and H2O minus. Or sorry, just H2O. What's going to happen here? My NH4 is going to donate a proton. Oh, so notice how one's a proton donor and one's a proton acceptor? Isn't that interesting? Nice little acid-base reaction for you. So what do we make? NH3 and H3O plus. So now what you have to determine to figure out, okay, well, which one's going to be more powerful than the other? You actually have to find the K values. So you have to find the KB value for this one, and you have to find the Ka value for your NH4. Whichever one's bigger tells you which one is sort of stronger, and will tell you if it's going to be acidic or basic. So if Ka is bigger than Kb, the solution's going to, this one, that means this one's stronger, which means it's going to be acidic. If Kb is bigger than Ka, then it's going to be basic. Okay, so how do we figure these out? Well, if you look these values up in the textbook, you can get the Ka for acetic acid, and you know that's 1.8 times 10 to the negative 5. So you can get that straight out of your textbook. So now to convert that to the Kb, because this is your Ka, okay, for that acid. So because I'm not writing that acid in my reactant side of the equation, I have to change it to Kb. So to find Kb, I use that equation that I gave you before, which in this case is going to be, Kb is going to be Kw over the Ka value. And I know what my Ka value is because I got it in the back of the text. So now I can calculate that my Kb is going to actually be 5.56 times 10 to the negative 10, I believe. I hope I did that right. 10 to the negative 10 or 10 to the negative 11? Of course, I don't have it right in front of me. Maybe you guys can check. Okay, we're 10 to the negative 10. Good. So there's my KB, and this is all for N. Oh, sorry, not N. This is my KB times 10 to the negative 10. This is my KB for CH3COO minus. So now, I'm going to do the exact same thing on the bottom in green, and I'm going to calculate the Ka of my ammonium. Well, I don't have Ka in the back of the textbook, but I do have Kb for NH3, and it's 1.8 times 10 to the negative 5. So when I calculate Ka, if this number is bigger, question mark, if it's bigger, then my solution is acidic. If it's smaller than this, then my solution will be basic. When you actually calculate it, what do you get? You get Kw over Kb, and you get, can I move that? 5.56 times 10 to the negative 10. Whew. Exact same number, which means they both have equal strengths, which means that overall, the solution, even though you have hydrolysis, is still neutral. All right, we're going to stop there, and you're going to finish up the rest of the examples in groups in class, and hopefully clear up any questions that you may have.